Welcome to KCSE 2024 Chemistry Paper 1, the ultimate destination for unraveling chemistry concepts, one question at a time. Together, we'll decode the mysteries of atoms, explore the magic of reactions, and tackle exam questions with confidence. Whether you're revising for your exams or simply curious about chemistry, this is your place to learn, grow, and ace your KCSE. Let's make chemistry exciting and achievable. Are you ready to take your chemistry revision to the next level? Let's dive in and start unraveling today's topic. In this video, I will be handling question 1 to question 5. All right, let's kick off our KCSE 2024 Chemistry with question 1. Question 1. Name the apparatus that can be used to, Part A, measure volumes of solutions more accurately than a measuring cylinder. This is a common and straightforward question, but it's essential for both practicals and theory. First up is the burette. This laboratory apparatus is a superstar in titrations. It's a tall, slender tube with a tap at the bottom that lets you release liquid, drop by drop. It's incredibly precise, down to 0.1 milliliters, making it perfect for experiments that need high accuracy. Next, we have the pipette. This is a highly accurate liquid transfer apparatus. For example, a 25 milliliter pipette delivers exactly 25 milliliters, making it an excellent choice for experiments where consistency is crucial. Then there's the volumetric flask. This flask has a single calibration mark, ensuring you can prepare a solution to an exact volume. It's a go-to tool for preparing solutions when precision is non-negotiable. Lastly, we have the syringe. You might recognize this from medical settings, but it's also incredibly useful in the lab. A syringe is great for measuring and transferring small liquid volumes accurately. Quick, simple, and efficient. Part B of question 1 asks to name the apparatus used to lower a burning piece of magnesium ribbon into a gas jar. This is an exciting practical question, so let's break it down. The answer is the deflagrating spoon. This specialized apparatus has a small, spoon-like holder attached to a long handle, which allows you to safely lower burning magnesium into the gas jar. It's especially useful in experiments where you're observing reactions in gases like oxygen. Why do we use the deflagrating spoon? It keeps your hands at a safe distance while letting you control the burning material inside the gas jar. It's an essential tool in practical chemistry, particularly when handling reactive substances. While the deflagrating spoon is the ideal apparatus for lowering a burning magnesium ribbon into a gas jar, other apparatus like a pair of tongs or forceps can also be used for this purpose. Tongs and forceps are handy alternatives when a deflagrating spoon isn't available. However, they don't offer the same level of control or safety as the deflagrating spoon, especially when working with open flames or reactive gases. So keep this in mind when choosing your apparatus. If you enjoyed this video, don't forget to like, comment, and subscribe to stay ahead in your chemistry revision. Let us move on to the next part of the question, Part AC, which asks to name the apparatus that can be used to store and keep substances free from moisture. The answer is the desiccator. This is a specialized container designed to store substances and keep them dry. It typically has a sealed lid and contains a drying agent, known as a desiccant, such as silica gel or anhydrous calcium chloride. The desiccator works by creating a moisture-free environment, which is essential for storing hygroscopic substances, those that easily absorb water from the air, or for protecting delicate materials that might degrade in humid conditions. Great! Let's dive into question 2. A radioactive isotope decays by either emission of alpha or beta particles. Part A of the question asks, explain why alpha particles have higher ionizing power compared to beta particles. First, let's break this down. Alpha particles are helium nuclei, 2 protons and 2 neutrons, giving them a positive charge of +2. Beta particles, on the other hand, are high-speed electrons with a negative charge of -1. The reason alpha particles have higher ionizing power comes down to 2 factors, that is, size and charge. Alpha particles are much larger and have a higher charge, +2, compared to beta particles, -1. This strong positive charge allows alpha particles to interact more forcefully with the electrons in atoms, knocking them out and creating ions. Alpha particles move more slowly than beta particles due to their larger mass. This slower movement means they spend more time near atoms, increasing the likelihood of interactions and ionization. In contrast, beta particles, being smaller and faster, have less interaction time with atoms and a weaker ionizing effect. Part B of question 2 asks to explain how alpha and beta particles can be distinguished in terms of their penetrating powers. The key difference between alpha and beta particles lies in their ability to penetrate materials. Let's look at each one. Alpha particles have a low penetrating power. They can be stopped by a thin sheet of paper or even a few centimeters of air. This happens because alpha particles are large and heavy, so they lose energy quickly as they collide with atoms in the material. On the other hand, beta particles have moderate penetrating power. They can pass through paper but are stopped by a thin sheet of aluminum, about 5 millimeters thick. Being smaller and faster, beta particles penetrate further than alpha particles. Let's keep going. Question 3. 3 bottles containing zinc nitrate, aluminum nitrate, or lead-2 nitrate have their labels missing. Describe a chemical test that can be carried out using aqueous sodium sulfate and aqueous ammonia to label the bottles correctly. This is a classic question in qualitative analysis, and I'll guide you through it step by step. First, test each solution with aqueous sodium sulfate. This will help identify lead-2 nitrate. When sodium sulfate is added to a solution containing lead nitrate, a white precipitate of lead sulfate forms. Neither zinc nitrate nor aluminum nitrate reacts with sodium sulfate, so no precipitate forms in these cases. Now that we've identified the bottle containing lead nitrate, let's distinguish between zinc nitrate and aluminum nitrate using aqueous ammonia. Add a few drops of aqueous ammonia to each solution and observe. For zinc nitrate, a white precipitate forms initially. Upon adding excess ammonia, the precipitate dissolves, forming a colorless solution. This happens because zinc forms a soluble tetraaminazinc complex. For aluminum nitrate, a white precipitate forms but does not dissolve in excess ammonia. This is due to the formation of insoluble aluminum hydroxide. Here's how to label the bottles. Use sodium sulfate to identify lead-2 nitrate. Look for a white precipitate. Use aqueous ammonia to distinguish between zinc nitrate and aluminum nitrate. For zinc nitrate, the white precipitate dissolves in excess ammonia. For aluminum nitrate, the precipitate remains insoluble. And that's how you solve this analytical chemistry puzzle. These systematic tests show the beauty of chemistry in action. Next, question 4. Consider the following equilibrium reaction for a mixture of gases in a gas syringe. Let us look at the equation. The forward reaction involves the formation of dinitrogen tetroxide from nitrogen, 4-oxide. The enthalpy change is negative. Part A of the question asks to give a reason why the enthalpy change is negative, exothermic reaction. So, the forward reaction is exothermic, meaning energy is released when 2 molecules of nitrogen, 4-oxide, combine to form 1 molecule of dinitrogen, tetraoxide. During this process, new bonds are formed between the nitrogen and oxygen atoms in dinitrogen tetraoxide, which releases energy. The energy released during during bond formation is greater than the energy absorbed to break any bonds, resulting in a net release of heat to the surroundings. Part B of question. State and explain the observations made when the pressure in the syringe is increased. The answer is, the yellow color intensifies. This is because the equilibrium shifts to the right, the direction with fewer molecules. Great! As we wrap up this video with an exciting finish where we're tackling question 5, the final question in this video. Let's finish strong. Part A asks us to write the equation for the reaction to prepare ammonia gas using ammonium sulfate and sodium hydroxide. In this reaction, ammonium sulfate provides the ammonium ions needed to release ammonia gas. Sodium hydroxide reacts with ammonium ions, breaking them down into ammonia gas and water. The leftover ions combine to form sodium sulfate, a byproduct, and that's the equation for preparing ammonia gas. Part B of question 5. Draw a labeled diagram of a setup of apparatus that can be used to prepare and collect a sample of dry ammonia. First of all, for the experiment to be workable, avoid loose connections of the apparatus, and heating is a must requirement. To collect dry ammonia, calcium oxide is used as a drying agent. Remember, being basic will not react with ammonia while drying. And finally, to collect dry ammonia, use upward delivery or downward displacement of air, since ammonia gas is less dense than air. And that wraps our video for today. Thanks for staying with me on this journey through KCSE Chemistry Revision. Be sure to like,